It's live now.
Great.
It's live now.
Then maybe we can start.
Yeah, Rohini, as a moderator, you can start.
Yeah, okay. So good afternoon, everyone, to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly hosted by South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University, SPPU. So before today's lecture will be delivered by Professor C.A. Babu from CUSAT. He's retired from there. And before he delivers the lecture, I request AVM retired Professor Ajit Tyagi sir, who is President SAMA, to please deliver the welcome address.
Thank you, Rohini, and welcome to all our participants, especially to the eminent speaker who is going to deliver a talk today and take the class, Professor C.A. Babu, who is a senior professor at CUSAT, and he had been teaching dynamic meteorology right from 1990s onward. And in fact, he had been driving factor for SAMA for starting this atmospheric dynamics online lecture series. He's also a member of our scientific committee. So thank you so much for your support extended to SAMA for organizing this program. And he will be delivering 3 lectures on important topics. First is today and followed by another 2. So that shows his interest in promoting atmospheric meteorology. And see, this is the basic foundation for all the topics of atmospheric sciences. And if we understand the dynamics, we can apply them very effectively in understanding the processes in forecasting and many other things, applications. So this is a very important program, and I'm happy that we have eminent faculty members who are delivering, and also operational people who will be delivering the talks in this lecture series. And another thing which is important is that we have started with the basics. The course has been developed very nicely, and this course also has the interactive system where we are requesting our faculty members to suggest some assignments, and so that involvement of the students to assimilate what is being covered becomes, it's not just like that you attend the class and then forget. No, idea is to follow it up. So this is very good, and we'll be having the exam also. So that is another step to see that whatever is being conveyed by our eminent faculty members is assimilated. And also we have a question answer session, so please make full use of it. Also followed by, if you have got even after that some doubts, you are most welcome to contact our source persons. They will positively try to make you understand those difficult subjects also. So this is a very good platform, and we had conducted 4 courses earlier which has received very good response. And this course also, we are finding that yes, all of you, though this is a little high-end program, and but I'm happy that all of you are taking interest, participating, and make full use of this program and today's lecture, which covers important theorems related to the atmospheric dynamics. So once again, thanks to Professor Babu for supporting this and taking today's lectures and 2 more. And I'm sure the students will be immensely benefited by your talk. Thank you.
Thank you, Professor Tyagi. Let me begin the session.
No, so we would like to
introduce you.
Yeah, we would like to introduce you then. Yeah. Thank you, sir. So now I would request Dr. Mili Goshni Lala from BIT Mesra to please introduce our speaker. Ma'am, I'll share the screen.
Yeah. Thank you, ma'am. It's my pleasure to introduce Professor C.A. Babu. Professor C.A. Babu had joined CUSAT as a lecturer in the Department of Atmospheric Science in the year 1990 and promoted to senior professor in the year 2018. His core area of research is Indian monsoon, apart from other streams of meteorology. He has been teaching dynamic meteorology for MSc Meteorology course of CUSAT since 1990. He received visiting senior research fellowship of the University of Malaya. He has also attended the Leadership Academicians program of UGC. He has completed his MSc in meteorology from CUSAT and then PhD in the same meteorology with the CSIR fellowship. He has many awards and honors in his name. One of such award is Senior Visiting Research Fellow from July 2008 to July 2009 at National Antarctic Research Center, University of Malaya, Malaysia. He has published more than 100 research articles in peer-reviewed reputed journals and authored 3 books and has guided several doctoral theses. Thank you, sir. We welcome you, sir.
Thank you.
Thank you, Dr. Millie. And I would request now, sir, to please share his screen and he can.
Okay. Welcome to the SAMA Atmosphere Dynamic course. Yeah. Let me start. Introduction. Any problem? Shall I start?
No, sir, you can, you can.
Yeah,
We
yeah.
have muted,
Yeah.
yes.
The topic is circulation. Circulation is a measure of macroscopic tendency for rotation. Macroscopic means in a small area, how much is the rotational tendency due to the relative motion as well as due to the rotation of the earth. So the circulation can be represented in an equation as capital C is equal to closed integral vector V dot D vector R. The unit of circulation is meter square per second, and circulation around a closed path in the 3-dimensional area can be evaluated as closed integral in bracket u dx plus v dy plus w dz, where the integral is taken along the closed curve at a fixed time. The circulation is related to vorticity as vorticity is equal to circulation by area, or circulation is vorticity multiplied by area. Actually, vorticity is a measure of rotational tendency about a vertical axis, and its unit is s raised to -1. Actually, in the case of circulation, a finite area of the fluid is also taken into account, whereas for vorticity, the area is not taken into account. Strictly speaking, we have to consider the direction for the circulation, because vorticity is a vector quantity. The direction of rotation counterclockwise, that is cyclonic about vertical, is treated as positive, and clockwise, that is anticyclonic, is treated as negative. Although circulation is considered as a scalar quantity by convention, its direction of rotation be treated similar to vorticity, because both of these properties are related. Or in other words, the direction of circulation counterclockwise, that is cyclonic rotation in the northern hemisphere, is considered as positive and vice versa. And as I mentioned earlier, circulation and vorticity are related. Vorticity is circulation divided by area. Now, let me explain the relation between circulation and vorticity on the basis of an equation. Consider a circular disk of fluid of radius r. If it is in rotation at an angular velocity omega about vertical axis or z axis, the linear velocity of the fluid is given by vector v is equal to vector omega cross vector r. For the circulation about the edge of the disk is given by capital C is equal to closed integral v dot dl as per the definition. So it is integral 0 to 2 pi in bracket omega r dot dl. The perimeter of the circle of radius r is equal to 2 pi r. So circulation C is equal to omega r multiplied by L in the limit 0 to 2 pi r. So circulation C is equal to 2 pi r square omega. And circulation by area can be evaluated as capital C circulation divided by area pi r square is equal to 2 omega. Thus, the circulation divided by the area enclosed by the loop is twice angular velocity of rotation and is the vorticity. Thus, we can relate circulation and vorticity as circulation divided by area is twice circulation divided by area is vorticity and is twice angular velocity of rotation. Next, let us discuss certain terminologies like absolute circulation and relative circulation. Absolute circulation is measured with respect to a fixed inertial frame of reference in which both the circulation due to relative motion and circulation due to rotation of the earth are taken into account. In the case of relative circulation, the circulation due to the relative motion, that is the rotation of the fluid elements relative to the Earth's surface by the velocity, is taken into account. Next, let us discuss Kelvin circulation theorem. Kelvin circulation theorem states that the acceleration of the circulation is equal to the circulation of the acceleration. In other words, Kelvin circulation theorem can be expressed as the acceleration of the circulation of a moving closed physical curve is equal to the instantaneous circulation of the acceleration. That is, suppose C is the circulation, dc by dt is equal to C of C acceleration or circulation of the acceleration. A physical curve is defined as a closed curve that consists of same air parcels at all instants of observations and is also referred as material curve. By definition, circulation is equal to closed integral vector v dot dr, and circulation of acceleration is equal to closed integral in bracket dv by dt close bracket dot dr. So acceleration of the circulation is equal to d by dt of capital C is equal to d by dt of in double bracket closed integral vector dot d vector r and is equivalent to closed integral dv by dt dot dr. Thus, the acceleration of the circulation of a moving closed physical curve is equal to instantaneous circulation of the acceleration. Consider the figure in which the continuous curve represents an arbitrary closed physical curve at a time t is equal to t0. After an interval del dt, the curve moves and changes its length, shape, and circulation as shown by red lines. The circulation of the velocity capital C is equal to closed integral vector v dot d vector r and is equal to dc by dt, that is acceleration of circulation is equal to dc by dt is equal to d by dt of closed integral v vector v dot d vector r is equal to closed integral d by dt of v dot dr. Because the integral is the sum of the contributions from the individual elements and therefore independent of time, since the curve always consists of the same particles. Therefore, the acceleration of the circulation dc by dt can be represented by the equation closed integral dv by dt dot dr plus closed integral v dot d by dt of dr. The first integral on the right hand side is obviously the instantaneous circulation of the acceleration, and second integral is 0. Second integral vanishes. Thus, the acceleration of circulation of a moving closed physical curve is equal to the instantaneous circulation of the acceleration. Next, let me start discussions on Bjerknes circulation theorem. Bjerknes circulation theorem is a combination of Kelvin circulation theorem and the equation of motion. Let us have the equation of motion. Equation of motion is same as the momentum equation, and let me refer the momentum equation in the Cartesian coordinate system. dv by dt is equal to minus alpha del p minus 2 vector omega cross vector v plus vector g plus vector f. This is vectorial form of momentum equation in the Cartesian coordinate system. The first term in the RHS is the pressure gradient force in the three principal axes. The second term in the RHS is the Coriolis force term in the three principal axes. And third term is the gravitational force per unit mass in the vertical direction. And last term in the RHS is the frictional force per unit mass. Since the frictional force is very small compared to the other three forces, on the basis of scale analysis, we can neglect the frictional force term. Accordingly, the momentum equation is dv by dt is equal to minus alpha del p minus 2 omega cross v plus g. And acceleration of the circulation is d by dt of circulation or dc by dt. So dc by dt can be written as in closed integral d by dt of vector v dot d vector r. Now let us substitute for d by dt from the equation of motion. So the acceleration of circulation dc by dt becomes closed integral in bracket the three terms in the momentum equation, that is minus alpha del P minus 2 omega cross V plus G. All these quantities are vector because they represent the pressure gradient force, Coriolis force, and gravitational force in the three principal directions, and dot D vector R as per the definition of circulation. So it is closed integral minus alpha del P dot D vector R minus closed integral in bracket 2 vector omega cross vector V close bracket dot D vector R plus closed integral vector G dot D vector R. The last term closed integral vector G dot D vector R is 0 since it is a closed line integral of an exact differential, and hence dc by dt becomes closed integral in bracket minus alpha and minus alpha del P dot D vector R minus closed integral in bracket 2 omega cross V. Now let us examine further details about the first time in the RHS, that is closed integral alpha del P dot D vector R. Here alpha is reciprocal of density or specific volume, and this equation can be rearranged in the three principal axes in the Cartesian coordinate system. Accordingly, we get closed integral alpha multiplied by in bracket I dou p by dou x plus unit vector j dou p by dou y plus unit vector k multiplied by dou p by dou z close the bracket dot product multiplied by in bracket vector I dx plus vector j dy plus vector k dz close the bracket. So the equation becomes closed integral alpha multiplied by in bracket dou p by dou x dx plus dou p by dou y dy plus dou p by dou z dz close the bracket. So this is equivalent to closed integral alpha dp. So our acceleration of the circulation dc by dt becomes minus closed integral alpha dp minus closed integral in bracket 2 vector omega cross vector v dot d vector r. Let us interpret physical significance of the equation. The acceleration of the circulation is contributed by two terms. One is minus closed integral alpha dp, and the second term minus closed integral 2 vector omega cross vector v dot d vector r. Thus, Bjerknes circulation theorem states that acceleration of the circulation is contributed by two terms, and the first term in the RHS closed integral alpha dp depends on the relative positions of the scalar fields of specific volume, that is isopignals and pressure difference. This term is 0 if the physical curve is located on a barotropic atmosphere. It is clear that closed integral alpha dp is the solenoidal term, and the solenoidal term vanishes in a barotropic atmosphere, or in other words, the solenoidal term exists in a baroclinic atmosphere. So, in a barotropic atmosphere, this term vanishes and hence there is no circulation as per the solenoidal term. Actually, minus closed integral dp by rho or minus closed integral alpha dp is the solenoidal term and is equal to minus closed integral in bracket alpha dou p by dou x dx plus alpha dou p by dou y dy in the two-dimension surface. Generally, we consider isobaric surface or pressure surface at different pressure levels in the two-dimensional. Or suppose we consider constant altitude surface like mean sea level surface, we consider on a two-dimension surface and hence we need not consider dou p by dou z dy dz in for this particular analysis for the time being. From the Stokes theorem derived for the horizontal velocity components u and v, we can write closed integral in bracket u dx plus v dy is equal to double integral in bracket dou v by dou x minus dou u by dou y dx dy. Stokes theorem states that a line integral can be converted into surface integral, that is area integral, where delta A is equivalent to dx multiplied by dy is an area element within the curve. The result is valid for the components of any vector, including pressure gradient force. Let us substitute alpha dou p by dou x instead of u and alpha dou p by dou y in the place of small letter v. So, minus closed integral alpha dp is equal to minus double integral in bracket dou alpha by dou x dou p by dou y minus dou alpha dou y dou p by dou x close the bracket dx dy. If we restrict to small area within which the derivatives assume constant mean values for the area, the contribution to circulation from the solenoidal term is dc by dt is equal to minus in bracket dou alpha by dou x dou p by dou y minus dou alpha by dou y dou p by dou x multiplied by small area dA, where dA is the small area. Thus, solenoidal term contributes to a change of circulation, and the circulation C can be evaluated to vorticity as C is equal to theta multiplied by dA, where theta is the relative vorticity. Solenoid is a peculiar property of fluid and no analog in rigid dynamics. In fact, the above equation is the two-dimensional form of Stokes theorem, which relates circulation to vorticity for the area of finite extent. Circulation is an aerial measure of the rotational tendency of fluid about a vertical axis, and vorticity is a point measure of the rotational tendency. In fact, minus closed integral alpha dp is a type of torque, that is force for rotational tendency, imposed on air parcels over the finite area by the baroclinicity of the atmosphere. The solenoid generated due to the isobars inclined to the isostates. Isostates are constant specific volume lines, and these isobars and isostates are inclined when there is horizontal temperature gradient or differential heating is responsible for the orientation of isobars and isostates inclined on a constant pressure surface and is responsible for the circulation. In a barotropic atmosphere, that is, density is a function of pressure alone, this term vanishes as it is a line integral of an exact differential. So the circulation due to solenoid vector does not arise in a barotropic atmosphere, as I explained earlier, in which the isobars and isostates are coinciding. The solenoidal term in the right hand side of the minus closed integral in bracket vector 2 vector omega cross vector v dot dr is Coriolis term. The physical significance of the term can be understood by considering a projection of closed chain of air parcels upon the equatorial plane as indicated in the diagram. I request you to refer the diagram given on the right top of page number C9. Actually, it is page number 9. By mistake, it is written as C8. It is page number C9. Consider x prime, y prime system in the equatorial plane. The actual lines are x and y, and projection on the equatorial plane is x prime, y prime. And y prime points towards the y-axis from the equatorial plane, and x prime points towards east from the equatorial plane as indicated in the diagram. From the diagram, it is clear x and y lines are eastward and northward from the station situated in the mid-latitude region, and its projection is considered in the equatorial plane as indicated in the diagram. So projection of a closed circuit on the equatorial plane is represented on the first diagram, and projection of an element of the YZ plane on the equatorial plane is shown in the second diagram. Consider x prime, y prime system in the equatorial plane, in which x prime is the projection of the x-axis on the equatorial plane and y prime is the projection of the YZ plane on the equatorial plane, in which y prime points towards the earth axis northward. Then dx prime is equal to dx and dy prime is equal to dy sine phi minus dz cosine phi, where phi is the latitude as indicated in the diagram. By similar projections, u prime is equal to u because u is equal to dx by dt, and v prime is equal to v sine phi minus w cosine phi, where small letter v is equal to dy by dt and w is equal to dz by dt. Here phi is the latitude. The Coriolis term becomes 2 omega closed integral in bracket v prime dx prime minus u prime dy prime. As one evaluates the integration around the circuit in the positive sense, that is in anti-clockwise direction, it can be seen that U prime dy prime is a contribution to a rate of expansion of the enclosed area, while V prime dx prime is a contribution to a rate of contraction of the area. Suppose capital F represents the area enclosed by the projection on the equatorial plane. The Coriolis term becomes minus 2 omega df by dt, where omega is the angular velocity of rotation of the earth. Next, let us discuss example for the circulation generated by these two terms to have a better idea. Let me have the features for the Coriolis term first. The role of Coriolis term. Suppose air within a circular region of radius 100 km at the equator with an initial velocity 0 is moved to the North Pole along an isobaric surface, preserving its area. The mean tangential velocity generated is minus 7 meters per second. The minus sign indicates the tangential velocity generated is anticyclonic in nature. Next, let me explain how do we get the tangential velocity with a numerical value of 7 meters per second and anticyclonic in nature. The circulation about the circumference can easily be evaluated as minus 2 omega pi r square multiplied by in brackets sine 90 minus sine 0 as per the equation. Here the air parcel is moving from the equatorial region to the polar region, and hence the numerical values 90 and 0. Therefore, the mean tangential velocity capital V is equal to capital C divided by 2 pi r is equal to minus omega r. The minus sign is involved in the original equation. By substituting the angular velocity value omega is equal to 7.292 into 10 raised minus 5 s raised minus 1, we can evaluate the tangential velocity as minus 7 meter per second. As air parcels acquire anticyclonic relative circulation of 7 meter per second upon reaching the North Pole. Next, let me explain the physical significance of the first term in the Bjerknes circulation theorem on the basis of sea breeze. So, role of solenoid time. The generation of circulation by pressure density solenoids can be explained in the case of sea breeze. Let us consider a coastal region with the ocean having less temperature. The mean temperature at the ocean, mean temperature over the ocean surface is T1. The air temperature just above the ocean surface is T1 and it is less than that over the land. So ocean is in the left side and land with high temperature T2 in the right side as shown in the diagram. This is the diagram. Isobars in bracket constant pressure are P0 near surface and P1 around 1 kilometer above the surface are represented by solid horizontal lines, and isostates are represented by dashed lines. Isostates are constant specific volume lines. In the diagram, isostates are not perfectly horizontal but slope and are represented by dashed lines. Let us apply Bjerknes circulation theorem to compute tangential velocity generated along a circuit in the vertical plane perpendicular to the coastline by the solenoidal time. As I mentioned earlier, the isobaric surfaces above the ground are horizontal with values P0 at the surface and P1 at 1 kilometer altitude, and isosteric surfaces are sloped downward towards land as indicated in the diagram. We can see that the temperature difference in this particular case is 10 degrees Celsius. The air temperature or the land minus the air temperature or the ocean can be treated as 10 degrees Celsius in the afternoon, and the horizontal extension of the area is 20 kilometer and vertical extension small letter h is equal to 1 kilometer. And by substituting the values in the equation, that is minus closed integral dp by rho is equal to minus closed integral rt dp by rho, by substituting p is equal to rho rt, where r is the specific gas constant for dry air and T is the temperature of the air. And hence the equation becomes minus closed integral RT multiplied by D of ln P, that is R multiplied by ln P0 by P1 multiplied by T2 minus T1 is mean temperatures for the air over the land, and T1 is the mean temperature over the ocean, and hence dV by dt is equal to capital R ln P0 by P1 divided by 2 into H plus capital L multiplied by T2 minus T1. Here 2 into in bracket H plus capital L is his circumference of the rectangular area, because the length is capital L and height is small letter h. After substituting the numerical values, we get the horizontal acceleration generated in the sea or in the ocean sea front is 7.1 into 10 to the minus 3 ms raised to minus 2, or the sea breeze generated can be evaluated as 25 meter per second in 1 hour, but friction and decrease of difference in temperature due to advection of air by the sea breeze will bring realistic sea breeze to have a value of less than 10 meter per second. Now time is 45 minutes past 3 o'clock Indian Standard Time. I am supposed to stop now because my class time is up to 3:45 p.m. Thank you for listening me. Let me wind up this session.
Sir, if you want to take more for 5-10 minutes, you can.
Okay. Okay. Thank you. Thank you. Yeah. I am supposed to explain about Vorticity features. Actually, as I mentioned earlier, Vorticity is microscopic measure of rotational tendency. And most of you are familiar with scale of velocity. Scale of velocity provides us rotational component of velocity in the three principal axes. And for meteorological application, the vertical component of vorticity, that is vorticity in the z-axis, is very much important because it is closely associated with weather processes. And the vorticity components in the x and y direction do not have any direct meteorological applications, and hence for atmospheric dynamics we consider the z component of vorticity and is usually represented by the symbol theta and is equal to unit vector k dot del cross v. So this is the measure of rotational tendency of air parcels in the atmosphere due to relative motion. Similarly, because of the rotation of the earth, we can experience vorticity, and this vorticity is referred as planetary vorticity. The planetary vorticity can be evaluated as small letter f is equal to 2 omega sine phi, where omega is the angular velocity of rotation of the earth and its numerical value is 2 into 7.292. I'm sorry, omega is equal to 7.292 into 10 to the minus 5 s raised to minus 1. And planetary velocity f is equal to 2 omega sine phi, where phi is the latitude of the station. As I explained earlier, for atmospheric dynamics, we consider the rotational tendency in the z direction, and hence we take 2 omega sine phi. Actually, for any solid body in rotation, velocity is twice angular velocity of rotation, and hence the vector form of planetary velocity is twice omega and its vertical component is 2 omega sine phi, and hence it is a multiplying factor sine phi involves in the planetary velocity. And absolute velocity is the sum of relative velocity and planetary velocity. For the generation of low pressure system, the absolute velocity is an important factor as per the Gray's paper of cyclogenesis. Over the equator region, the planetary velocity value is very small because the latitude of the equator region is almost zero. That is why the low pressure systems are not generated over the equatorial region in comparison with that over the mid latitude and polar region. But whenever the relative velocity is very high, the absolute velocity is sufficiently large for the generation of low pressure system, even though such a situation rarely occurs. So the absolute velocity is the sum of relative velocity and planetary velocity, and planetary velocity value is generally small in the equatorial region or almost zero, and it is small in the tropical region. Next, let me introduce potential velocity. Potential velocity is a ratio of absolute velocity to the depth of air column in the atmosphere. The potential velocity value plays vital role in certain occasions for the transformation of weather system, especially when the air column encounters hilly region or mountains. In such situation, the air column height or depth changes. Further details about velocity will be discussed in the next class on 15th April. I personally feel it is good to have short note or the PDF file on the display for explaining features as well as for understanding the equation in a better way, and hence I do not want any further adventurous task without proper PDF file. So let me stop the class for the time being. I am ready to answer a few questions since the time is available for another 10 minutes.
Thank you, sir. So before we go for the question answer session, I would like to have request everyone to switch on their cameras. So we will take the photo. So can you please unshare the screen? Tyagi sir, if please switch on your camera. Hello, Dr. Mohan. Tyagi sir. So Ashwin, you can take few pictures. Okay, Tyagi sir is here. Yeah. Thank you. So now I request Ashwin to please moderate the question answer session.
Thank you, madam. So there are few questions. First, go with Aisha Mohanty. So the question is, what is the solenoidal term? Why do we need this for circulation? Why we are using specific volume alpha?
Yeah. As I mentioned earlier, the solenoidal term arises in a baroclinic atmosphere. Baroclinicity is arise because differential heating, and in such a situation, the baroclinicity can be assessed, or intensity of baroclinicity can be assessed on the basis of how much is the angle between isostats and isobars. Isobar is a line or curve of constant pressure, and isostats are line or curve of constant specific volume. Instead, we can also treat isopycnals. Isopycnals are line or curve of constant density. Due to the differential heating or temperature gradient in the atmosphere, the isobars and isostats are oriented with an angle, say alpha. Depending upon the intensity of differential heating, the angle alpha is large. On the other hand, suppose the differential heating is zero, the isobars and isopycnals are coinciding, the solenoidal term does not arise. I am ready to explain further on the basis of sub-questions.
Thank you, sir. Next question is, can I use the vorticity equation for a tornado?
I think so. And again, in the application is not mentioned. Simply said tornado. I think so.
Okay, sir. Okay. Thank you, sir. Next,
Further questions?
can you please explore the application of the theorem?
Which theorem? Bjerknes circulation theorem? I have already explained the with examples the application of Bjerknes circulation theorem. Suppose any further question on the examples, I am ready to elaborate further.
Yeah. Thank you, sir. Thank you. The next question is from Johnson. Whether vorticity or circulation is valid above planetary boundary layer or below or both?
Both. The circulation as well as vorticity are important for the weather system, not only in the planetary bound layer but also above planetary bound layer or wherever weather processes take place from surface to top of troposphere. Generally, weather systems generate and transformation take place in the troposphere, not only in the planetary bound layer but also above the planetary bound layer in the troposphere, and hence both vorticity as well as circulation are important in the planetary bound layer and the layer above planetary bound layer.
Okay, sir. Okay. Thank you so much, sir. So there are only these questions, so we can stop
Let us
question answer. Please.
invite further questions via email or
Yeah.
any other means, so
Okay.
that after going through I will try to answer according to the situation.
Yeah. So attendees can also email any further questions to Professor C.A. Babu. He will be happy to answer your questions.
I will try to answer genuine questions or reasonable questions. I fully agree. There are a few questions which may not be clear from the questions itself, and hence I may not be able to answer. And I do have many unanswered questions in my mind. And Holton is already died, no email to heaven, and I am unable to certain questions beyond my imagination or capacity.
Yeah. Sure. Thank you so much, sir. Thank you so much for a great lecture.
So let me invite all attendees for the class in the next Saturday.
Yeah.
Yes, thank you,
Thank
sir.
you all.
Yes, sir, wait. Before we close this session, I would like to give some statistics. So up till now, 120 participants have given their attendance, and 93 participants have claimed this lecture to be excellent or very good. So this itself says how good the lecture was. Thank you, sir. And now I will request Mrunal Naik from IITM to please give vote of thanks.
Thank you, ma'am. I'll just share my screen. So on behalf of the organizing committee, I would like to thank each of you for your contribution on the 12th lecture of weekly online series of atmospheric dynamics and its application in atmospheric science. Firstly, I would like to thank AVM Professor Ajit Tyagi sir for giving a welcome address and a brief information about this lecture series. My deepest appreciation goes to our speaker of the day, Professor C.A. Babu sir, retired from the CUSAT, for delivering a very informative lecture on Stokes theorem, circulation absolute and relativity, Kelvin circulation theorem, Berg's circulation theorem, and potential vorticity. I also thank Dr. Rohini Bhava for moderation of today's session and Mr. Ashwin Zada for efficiently managing the question answer session. I also want to thank all the panelists and EC members for their guidance and constant support for every minute details. I extend my thanks to all participants and attendees who joined us from each part of our country. Last but not the least, sincere thanks goes to team member of Savitribai Phule Pune University involved in the organization of this lecture. Thank you, everyone.
Thank you, Mrunal. And now Tyagi sir, if you want to say something, I request the participants to please email the questions if they have any to Professor C.A. Babu sir. And next week, he will again be delivering the lecture. So on 12th April, we will be meeting him again. Sir, you want to say something?
Yeah, Rohini, thank you, Professor Babu, for respond to your questions and willingness to answer even after the session. If some of the students have some more doubts, they are most welcome. And this is what makes our lecture series very, very useful with the kind support from the source person. So thank you so much, Babu, and also thankful to the Rohini and the organizing team, both from VIT Mesra and of course South Ribai Phule University, IITM. It's a teamwork. So let's keep it. And next lecture, we look forward to Babu Sahib again. Thank you.
Thank you all for your encouraging words and keen attention and organizing the program nicely. Thank you all.
Sir, and sir, we would like you to send us one assignment problem or short question where an answer can be provided. So that
I
we
will send you via email.
Yes, sir. So we'll circulate this to the participants and
Yeah,
they will
okay.
be sending us. So thank you, everyone. I will